This lab is about HiFrog.
We are having Sepideh and Martin assisting with the lab.
And today we're mostly going to focus on what you've seen in lecture 1, lecture 2, and lecture 3 in the video. The internal steps of the tool are hidden from the end user, but you should be aware of them because technically speaking, they are the options of the tool which you can choose from when running it while analyzing your system. And naturally, there is a large selection of options due to the large infrastructure which our tool supports. Let me just very briefly recall once again what's happening there.
This is a fully automated technology, so it could be treated as a push button technology. We provide to the tool the programs we want to verify together with some properties to check. And then the tool does all the magic without any user interaction and reports us if the safety property is satisfied or not, meaning that if the property holds, then there is no error, there is no bug in the system. Otherwise, it tells us the property fails and generates a counterexample demonstrating the failure of the system. As I explained in my video lectures and during the discussion sessions, it's a sophisticated technology which interleaves SMT solving to make sure this could be done effectively. So essentially, HiFrog employs incremental analysis. So it's trying to compute some artifacts, some computational histories, which we call function summaries, to help us to speed up verification of the system against many possible properties to be checked. So only once on the very first run, we are verifying system without any computational histories. If the check succeeds, it's a bootstrapping step. Then the tool automatically computes summaries for each function used in the system. And for the next run, whenever we need to verify the system against different properties, instead of doing complete full encoding of the system, it's going to use summaries whenever they are possible to be used. So the summaries could be computed for different encoding levels. Since it's a SMT-based technology, we have the choice of encoding our program using different precision levels. So it could be something light or something quite heavy. Light in terms of how much computational resources is required to solve the formula by the corresponding solver. So we can have propositional encoding, we can have linear arithmetics, we can have uninterpreted functions encodings. So the tool gives us all these options to choose from. And correspondingly, whatever the choice of encoding of the program, we will compute the summaries following the same encoding representation. Solver uses interpolating procedures for the corresponding logics to compute the summaries. So it's over approximating procedures. They're trying to simplify the representation of the system. And it might be that this over approximation introduces spurious behaviors. Then the tool will try to refine, it will analyze the failures and refine them if it was detected that the failures were spurious. So it will gradually, throughout the run of the tool, do the magic of finding the appropriate level of encoding for the summaries. Today, lab is about for you to get acquainted with the tool, trying to use it, run it. And yes, technically speaking, you don't have to interact with this, so you can just provide the input and see what it tells you. But we designed for you a number of illustrative examples to help you to understand what's going on how exactly things are happening. So you can choose different levels of encoding, you can choose different interpolation algorithms to compute different summaries, and so you can also provide summaries yourself if you have some useful domain knowledge, and you can instruct the tool to use your summary instead of automatically computed summary. So all of these things we will illustrate today, so you can become acquainted with the tool and really understand what's happening. So we decided that we will just gradually start with interactive activities with you by providing you with the tool and some examples. So Sepideh will run this illustrative session, and we will just go as fast or as slow as necessary just to make sure everything is clear to you. Martin is also assisting. He will be looking at the chat session, and if you have any question, he will try to react as quickly as possible to help you to sort out the questions. If needed, we can also create a breakout room for those who really having troubles and something does not work. So separately, we can help this group of people to get up to speed with the demo. But in our previous run, just an hour ago, we already realized that actually we didn't need a breakout room at all. So everything was sorted out by just chat room questions. Well, that's, I guess we will start this way. So any questions so far? All right, then let's get our hands dirty and play with the tool. So I will let Sepideh share her screen with you.
So, hello everyone, I am Sepideh. I'm happy to be here to show you some interesting functionalities of HiFrog, and we are going to learn how to verify our program. I try to guide you through the commands that we collected already for you, and we are going to follow this command. And I already sent the link of the examples that we are going to use today. So if you haven't downloaded already, please do. And if you did, the name of the file is lab_HiFrog_approver. And if you go inside, so you will see two subdirectories. Today, we are going to use only HiFrog demo directories example. So let's navigate to the directory. Here you will see a bunch of C examples. And if you see any files started with underscore summaries, please remove it. So that will prepare the environment for the HiFrog to be clean and to start with verifying a new benchmark. If you have any questions with setting up the tool or downloading the example, let us know. Otherwise, we can continue running benchmarks with the HiFrog. So I assume everything is fine. So let's start with the simple example. You can also open it in your virtual machine, and we can together look what this benchmark is about. So there is a main function here. There is a call for function sum. So if you go inside the implementation of sum, you will see that there is a non-deterministic value. So this is basically a function without any declaration. So what it does, it just returns any non-deterministic value with the type unsigned integer. And this function iterates 100 times, and in the end returns the summation of those non-deterministic values. So there is another call for the exact same function, but this time it checks, it would like to know if b is greater than 0. And in the end, it would like to know if c is greater than 0. So basically here we have three assertions. So let's ask HiFrog to verify if the first assertion in this program is safe or no, if it holds or no. So for that, I'm calling HiFrog binary and specifying the name of the benchmark. ex1_LRA. So there is an option in the HiFrog which is called logic, and here we can specify different logics. So as we have already seen in the lecture, we can encode the C program with different logics. So this time let's use QF-LRA, which stands for quantifier-free linear real arithmetic. And let's specify which property we would like to verify. This time, let's say we take claim number 1, which checks first assertion in the program. And there is an option that tells we can save the generated summaries into a file. Save summaries. We can specify a name. So let's skip this conversion for just convenience to use the name of the file starting with double underscore. I'm calling it underscore summaries. So we are good to go. Let's click and let's see what happened. First, HiFrog started to, of course, parsing the input C file. And after some pre-processing, which relies on cProver framework, it checks first claim. And here there is a note that for this run, HiFrog uses a specific interpolation algorithm for generating the summaries, and that's called decomposing Farkas algorithm. So later we will see that how we can also change the interpolation algorithm for generating the summaries. And here each function gets inline. So you see the main function is inlined, so do some functions. And after creating the single static assignment, which in total is this amount of steps and some optimization over the steps, so the generated logical formula is passed to the solver, and solver returns that this is unsatisfiable. That means that the error that we asked is unreachable. So that means that the first claim, the first assertion in the program is safe, false actually. In this stage, the tool can actually start generating the interpolants because we have unsatisfiable proof, and based on the Craig interpolation, it will generate interpolant, will stored as a summaries. Yeah, you may ask that, hey, how does the summary looks like? So we can take a look. This is the file that I called it initially. In the beginning, you see that the logic is LRA. That's the one that we also used for encoding the C program. And here are a bunch of declaration, which you don't have to go. So let's go to the interesting part of the summary, which is here. Basically, define fun follows the name of the function that has a summary. And here are the arguments for specifying the start point of the function and the end point. And this is the body of the function. So it says that the return value has to be greater than 0. So as you remember, the program had 100 times iteration over the non-deterministic value. But as you see that the summary, that means the relation between the input of the function and the output is just such a nice and compact summary. This is stored in the file. Why not using this nice compact summary in verifying other assertions? So let's say initially I verified claim 1. Let's take this time claim 3. And what I have to tell HiFrog to load the summaries. So this is the default. So if you even also didn't write in the option, so it will automatically look for the generated summaries into the environment. So we can run and let's see what happens. So remember, previously all the functions were inline, but this time you see that for the function sum, the summary abstraction used. instead of inlining. So what that means that instead of a precise encoding of that 100 times iteration, so basically it just reused that nice compact summary, which was greater than 0. And here you see that all of a sudden it was just successfully reused. And you see that we are happy and verification is successful, right? Of course, this was a example. Everything here was just happy, but it can be a case that summary is not sufficient for verifying a property, and the tool will start automatically refining the abstraction. Any questions so far?
I have a question. So,
Sure.
where do the claims come from? Are they the assertions or?
Yes.
So
yeah, the claim means the assertion in the program. Claim 3, for instance, the third assertion in the program.
Okay, yeah,
So for instance, if you run HiFrog show claims, so it will exactly tell you that the first claim is actually the first assertion in the program, the second is the second, and the third claim is the third assertion. So let's this time not to play with the toy example. Let's use some more interesting and real world benchmarks. So don't forget to clean the summaries, because this time we want to verify a new benchmark. So let's prepare the environment. And I'm going to show you one benchmark from the Linux device driver. So this is the benchmark. It's around 5,000 line of code, and let's see if there are any assertions in the code. Yes, we have some assert 0, and yes, interesting assertions, you see. But of course, by looking into benchmarks, we cannot manually tell which assertion is safe or which not. So let's ask HiFrog to help us. But before running that, let's see how many assertions exist in the program. So if I run show claims again, yes, 79 assertions. That's quite a lot. Let's verify a couple of them. Call for the binary, specifying the file disk.c. Let's verify the first claim, and let's specify the logic. Let's take again QFLarray and save the summary somewhere. Yes, I think we are good to go. Let's see how quick this would be. Perhaps, yeah, given the 5,000 lines of code, we have to wait a little bit. HiFrog to inline all the functions with respect to the claim 1. Okay, we see here that the number of generated summaries are 172, which is stored in the file, and the result is successful. So the first claim actually holds. So the program is safe with respect to that property. And the total verification is almost 30 seconds for this claim. Okay, so since we wait a little bit for this and we spend some effort for this, so why not reusing this effort for verifying other claims in the same benchmark? Could you do it by yourself if you have already?
I got the first one to run. The disk.c said it couldn't open the file, so I'm still working on it.
So are you inside the HiFrog demo directory?
Yeah, I'm in the same directory where I ran the first example. So I ran the first example one with the claim 1 and claim 3, and that all looked good. And like I see the file disk.c, so I'm not sure why. It's probably just something on mine. And
you also cleaned the environment.
I spelled disk with a C, not a K, so that's my bad. I'm sorry.
No worries.
So what if you run exactly the same command again? Would it go much faster?
Yeah, let's try it. It should. because this time it should reuse the previous summaries. But let's do some interesting exercise. Let's, for instance, verify claim number 79, the last claim, because we already know that the result of claim 1. So let's see if verifying the claim 79, we can reuse some, at least, information from the first run and to speed up the verification time.
Shockingly, mine worked when I spelled the file name correctly.
Any luck? Somebody?
Sorry, what was the question?
Anybody succeeded verifying claim 79?
Mine says verification successful. Yeah, so it looks like it was able to.
Okay, how much time did it take for checking the claim?
Let's see.
I got a success too.
So did you record the timing of the first claim and claim number 79? So do you see the time difference?
The first one was, I don't know what the units are.
Seconds.
Okay, so yeah, 30 seconds? No. And then the second one was definitely faster. It says solver time 0.218. I'm sorry, I don't totally know how to read that number. Is that 218 minutes or?
And then there, in the end, you see the total time for checking.
Oh, I see. Total time for checking this claim for claim 78 was 8.71 for me, so it ran pretty darn fast.
So almost 4 times faster.
Somewhere should be report how many summaries were substituted. Somewhere in the log file, right?
Yeah, do you see it?
Oh, mine says function summaries for 160 calls were substituted successfully on my second one.
All right.
Yeah, that's the reason why it was so fast this time. So instead of encoding the functions again, so it just reused the previous summaries.
To be clear, that's disk with a K. Disk with a C runs in infinite time and used 0 summaries, so that one didn't work very well.
Okay, so if there isn't any question on this, we can move on to...
Yeah, can I just ask a high-level question?
Sure.
So it's substituting function summaries. I was just curious if you ever played with the granularity of that, like maybe smaller towards like basic blocks or something, or if there's like kind of a size of that makes sense for the most reusability.
Yeah, in the HiFrog, so we have a paper in SAT 2017. There we substituted we changed actually the encoding based on the instruction. Whenever you had some instruction that you knew that this has to be refined, so you substituted with something more precise. So, but for the function summarization, HiFrog is only able to generate summaries for the functions, not like basic blocks.
So can I also ask a high-level question related to this?
Sure.
Just to clarify that I understand correctly what these function summaries actually are. So since they are over approximations, the summary basically encodes all the possible behavior of the function plus possibly something else.
Yes, exactly.
But it has to include all the behavior of the actual function.
Yes, and it can be the case that since it's over approximation and can include some spurious results, and HiFrog is able to automatically identify those and to refine it. In those cases, the summary is identified as not being useful, and then there you have to either encode the entire function precisely, or you change the theory to the stronger one. So we'll see some examples on it exactly. So if this happens, HiFrog will warn us that this violated assertion would be spurious. So we have to be careful.
I actually have a question. I tried to check another claim with the HiFrog, the number 72, and it seemingly hit a bug. So I would like to ask if you could repeat the experiment and maybe give us some hints on the remark you can draw 72.
Yes.
Without summaries. Oh, you can.
You already.
It doesn't change anything.
So did you clean the summaries from the repository? Because even if you don't specify this, it will look for this file in the repository. So do you want me to run this without any summaries?
Please, yes.
Okay, let me.
Yeah, I think she's saying you have to delete the file before you run it. So did you delete that file before you ran yours?
No, I didn't delete it.
So then it will reuse it by default, I think is what she's saying.
Yeah, it will reuse. Yeah. Otherwise, if you get assertion violated, so you will see a warning that this could be spurious.
It's a warning, and the message is it says it's possibly due to a bug found. Warning possibly due to the abstraction. So I would like to know your the remarks you could draw from this warning.
Yeah. The point is, since you didn't have summaries in the repository, right? Or if you already had and HiFrog already invalidated, but still the result is violated, since you are using QFL array for this encoding, and this is known to be abstract theory, that means that your result could not be 100% correct. So you have to double check with some more precise theories like propositional. That's what the message says, the warning. So basically, if the result is safe, so you can blindly trust the result of the tool because it's over approximation. And if it's safe in any other more precise theory, it will be safe again. But if it's unsafe, so you have to go to check more precise theories.
Okay.
Is that clear?
Yes.
Sure. Any questions?
Does HiFrog work on the level of analyzing the C language, or does it understand the C language, or is it compiling it?
So HiFrog takes a C program. It does some pre-processing, and for this part, it relies on cProver framework, if you know it from the export group. And then based on the symbolic execution, creating a single static assignment, you'll create a logical formula. So that's the flow from the C program into a logical formula. Did I answer your question?
Yeah. Okay. Thanks. I wonder how many other languages can you use HiFrog?
No, it only supports C program. Okay, so we have seen verifying some toy and real example with QFL array. So let's try different theories. For instance, let's take example product. Let's look at this example. There is again some non-deterministic value, and there are some assignments. Basically, all the A, B, C, D are equal, and then two function calls for the prod with the same arguments, basically. And what the prod does, you see this nonlinear multiplication over these two variables, which is known to be very expensive for the propositional logic, and also linear real arithmetic cannot verify this, right? But if you look carefully, so since you are calling these two functions and the return value is exactly the same, because you invoke both functions with the same parameters, and then in the end you just check if the return value is equal. So it doesn't matter really what's going on inside the function. So all we care is if the function is invoked by the same parameters, if the return value is equal or not. And this is a perfect scenario for the uninterpreted function logic that can easily verify this. But while if you verify this with the propositional logic, it won't go through. So I will ask you to try it first with the propositional logic, as I'm doing also here. You will see that you have to just wait for hours, and then you will need to kill it without any result. Yeah, this is what I just explained. So with the propositional logic, it seems we wouldn't get any result soon. So let's verify it with QF, UF, with uninterpreted function. All I need to specify the logic, UF, UF, and the name of the file. And if I don't specify the claim, it will automatically take the first claim. And as you see here, in a fraction of seconds, so the result is successful. And yeah, all just went well without any bound.
Sorry, could you just hit the up arrow so I can see the command you ran one more time?
Sure. You have also this file. You can also look up to the file, because I know there are tons of options, and you need to repeat a couple of times to remember. This time I only changed the logic. So here we saw the beauty of use of uninterpreted function, but the story is not happy and always like this. For instance, if you verify some benchmarks that contains some arithmetic operation, and their UF would not give you a correct results. For instance, in this benchmark, EX underscore a choice. So here you see the return value of this function is linear operation, and the assertion also requires understanding of this comparison between these two variables. And if you try to run such example with UF, let's see what will tell us. And each time remember to clean the repository. Again, a call for HiFrog, specifying the logic, name, and claim. So if I verify this example with QFUF, you will see that the assertion is violated, and you see here a warning that says that this is possibly because of the abstraction. So since here there wasn't any summary to use, and we were using QFUF, so that means that the use of the abstract theory was not enough to verify this benchmark. So we have to switch to some more precise theory like L-array. We can run it with L-array. All I have to do is just changing the logic. The rest stays the same. And yeah, let's see. Yeah, as expected, because the benchmark was small and I knew it. So the result is safe, and here we can see that 3 summaries were generated out of this safe run, and we can reuse this information again for the next verification as if we want.
So just to clarify, we need to delete the summary file when we're sort of switching to a new file, right? But if we were maybe changing like the logic type or something, but staying on the same file, we would want to keep that information to try to reuse it. Is that correct?
For now, let's clean every time. So later
Okay.
I will show you some examples that the tool can
So if I was running the same
yeah.
type of logic on the same file, keep the summary file.
Yeah.
In pretty
And
much
you
every
just,
other case, clean it.
yes, and same file, but you want to verify different assertions in the file.
Right. But
there
I guess
you need summaries.
if I was switching from like the QFUF to QFLRA, I should go ahead and clean as well, just to have a good starting point. Okay,
Yes.
thank you.
Yes. Yes. Any other questions? If not, I would like to show some also basic but interesting features of HiFrog. That is the generation of the error trace. So for instance, if you look into this benchmark, EX_unsafe. This is exactly the same benchmark, but this time I changed the assertion so that it's unsafe this time. But let's see if HiFrog can understand this. And binary of the HiFrog, logic, the claim, and the name of the benchmark. So if I run HiFrog over this benchmark, yes, we see that HiFrog generated a counterexample where it says that if A is -1 in line 17 and B is 0, D gets 0, and there this assertion gets violated. So you see the mapping of the concrete evaluation of each variable is printed here, and you can see this trace, and you can go back to fix where the failure happened.
So when is it able to give us these counterexamples? Is that something it can do in general, or is there specific cases where it's able to sort of understand what happened?
Could you repeat your question? I'm not sure I followed.
So when verification fails, can it always give us a counterexample? Or
Yes.
are there particular? Okay, I guess that answers my question then.
Yes. Okay, let's move on with some more interesting features of HiFrog, which you have seen one example from the lecture, and that was the use of user-defined summaries. So this time we would like to plug in our knowledge by looking into the functions and to inject the summaries and to help HiFrog to verify it if none of the theories was not able to verify. For instance, this example that you have seen also before, you see this nonlinear function here that returns the sine squared plus cosine squared, and the return value of the nonlinear function is checked if it's equal to 1 or not. So from the basic mathematics, we know that this operation is equal to 1. So why not to use this information and help HiFrog to verify this? Because as it is, if I verify this benchmark with any logic, so it won't get through, because this is nonlinear and it requires a nonlinear solver, which is not supported in many solver, and it's quite costly. And LRA and UF is also not able to verify it, right? But as a human, we know that this is equal to 1, so we guide the solver to verify it. So let's see how we can do this. First, I need a template of the summary that be able to inject my knowledge in it. For that, I need to use this option, list templates. And I can specify the logic, for instance, array, and the name of the function. Okay. If I run this, so the tool will generate a template that I can open it. And this is the declaration of the nonlinear function. And here you see true, which we can modify this body and to insert our knowledge. So the return value of the function has to be 1, right? As we discussed. What I'm doing, I'm deleting this true and opening in a prefix notation. I write the nonlinear value should be equal to 1. That's it. the rest will stay the same. I'm saving the file and let's verify it. With, okay. Yeah, you see that the verification is successful and the function summaries for one call were substituted successfully. So basically our summary was useful to verify this benchmark. So now I would like to ask you.
So sorry, I have a question.
Sure.
Could you show the source code of this SYNCOS program again?
Sure.
So now this is computing with doubles. So wouldn't the actual output of this function nonlin possibly be something other than exactly 0, but something very close to 0?
Yeah.
No, I mean one.
Yeah, I think you are talking about the exact run of a C program, right? Yeah, that's true. This is just for the demonstration. Yeah, I totally understand your concern. And this is just the toy example that demonstrates you can inject your summary. And we here assume that so there is no overflow and this so we are not verifying this mass.h library. So all we verify just this function. For instance, if you look into the other benchmark that I have, so for instance here, this is again a very crazy complicated operation that none of the theories could handle it. Because as I said, it requires a nonlinear support for the solvers, which is very costly. So by looking into this function, can you guess what should be there, if there is any invariance, so if you can deduce any summary that's always true for this mod mult function?
Well, that mod should just undo the multiplication and I should get A back, right? Is that what you're asking?
Are you sure? A or, because the result of this multiplication over mod B.
A times B?
It's 0 if B is strictly positive.
Yeah, exactly, 0. So now I'm going to ask you if you can generate a template and to use this information. Yeah, now it's your turn. So first you need to create a template for the summary and then modify it with your nice understanding the behavior of this expensive function.
Can you show your summaries non-lin again?
Sure.
I think I wrote something wrong.
So all I changed was...
It looks like I did the same thing, but it didn't.
So could you type your summary to the chat?
Okay.
It's fine, yes.
Sepideh, maybe you can continue and I can try to take over Andrew.
Okay, so Martin, yeah, thanks. So he will help us. So you can, yeah, work with Martin separately and we can move on if it's okay. Is there any other question regarding the user provided summaries or?
Yes, so something I thought of now was, so what if the user provides a summary that's actually not true? So then that would just break any verification guarantees.
Yeah, that's a very good question. Because if user provides a summary, so HiFrog will trust it and it will use it, and all of a sudden if the assertion gets violated, yeah, you cannot do anything. I'm again opening the function where it was returning some operation over B. But since here we have B, and again, it's mod over B, so we know that the result is always 0 from the mathematics. You can use this information, verify it. Because otherwise, none of the propositional or L array by itself cannot handle such program. If someone, there's a question. So the question from the Emily asks, the assertion are only the specification, right? Yes. So the assertions are those you already hard-coded in the program. So it can be any safety properties. I'm not sure I followed your second question. Some intermediate assertion. I don't think HiFrog supports this. So all the assertions should be hard-coded in the program from the beginning. So there is no intermediate assertion. So for instance, there could be overflow check, but you have to also encode it in the program.
So most likely you've been influenced by the lectures on theorem proving, where you are guiding the proving procedure by providing lemmas. No, it's a different technology, what we are doing here. So it's really a push button technology. You don't need to guide the tool.
And the question says, HiFrog might do loop unrolling. Yes, this is a bounded model checking. And if a program contains loop, so the user has to specify some bound, and the formula will be created up to that bound. And then within that unrolled formula, for each fraction of the code, which is a function, so you will generate a function summary. So that's the summarization part in the HiFrog. And yes, you will get the correctness up to that bound. So that's the bounded model checking. But as you saw before, for instance, in verifying the disk, right? You remember we verified first claim and claim 79, but there we didn't specify any bound. There wasn't any need to unroll the program because by itself it was finite. So basically, such programs are correct for infinite bound. I hope I responded all the questions in the chat. So speak out loud if I missed something.
I actually have a question about the cprover assume macro, and I wonder how it interacts with HiFrog, and is it possible to circumvent the direct interaction with the template and just use the cprover assume to help the HiFrog?
Yeah, exactly. So when you create a non-deterministic value, and immediately after that, if you limit the range of the random values, yeah, that would definitely help the HiFrog to decrease the search space. So yeah, that's, as you see in some of the benchmarks, we already used the cprover assume.
So for example, the manipulation we did on the template could be equivalent to just adding the cprover assume that that m is equal to 0 just after the mod malt operation in the mod malt file. Is it the same? Will it have the same effect than modifying the template?
Yes. You already tried this, right?
No, just no.
Yeah, I think it does the same things as injecting the zero summary manually for the
because it's more readable than modifying the other files like cryptic and
yeah, I agree. The playing with the summary, it's a bit tricky, but this lab is just for the demonstration, so we intentionally ask you to play and sometimes gets frustrated by knowing all these options and changing the theories. But the goal of HiFrog is not to bother the user at all. So it's very like a push button technology. So the user is only to provide the file and just click a button, and the tool is doing all the right choice of the theories and choice of the summaries, everything. The tool automatically handles it.
So I have another question about data structures, for example, linked lists and trees or other branching structures. Does HiFrog support theories dealing with this with such a data structure, or just it deals with very low level pointer arithmetic and etc.?
No, those containers from the standard libraries, especially the ones that uses pointers, they are abstracted away. So basically, you treat them as abstraction, and all of a sudden, if the property being checked doesn't depend on those specific lines of code, you can verify. Otherwise, you get assertion violation, and with a warning that because of the abstraction you made, you got this result.
Okay, thank you.
I can go with one more example. Yeah, and then we wrap up this session. So yeah, this was all about using different theories and changing the summaries. I would like to demonstrate a little bit more low level to the solver that does all this work to generate the summaries, and we want to tune the strengths of the generated summaries. So if you take this comment I provided here, so these parts we have seen already, the binary and the logic and the claim, and you see that in the benchmark that I will show you, we use this ITP LRA algorithm to the 0. If you look to the manual of the HiFrog, this stands for the strong summary that will generate us a summary, which is the stronger one. And we will going to store it into this file. So just quickly, I'm going to show the example. There is a function call for the ABS, which performs the absolute, always returns something positive. And then the assert checks if the return value +2 is greater than 0. So if I run the command, and I'm using this verbose solver 2, which I ask the solver to print the interpolants in the standard output. Let's see what happened. So this is just the normal business. So the important part starts from here. You see that the generated summaries, basically the interpolant, are here. If you make a record of this, let's save it somewhere here. If we change the strengths of the LRA interpolation algorithm, so this time to 2, and to save it to another file, let's call it weak, because I know that based on the manual of the HiFrog, option number 2 generates a weaker summary. And yeah, that's it. So let's run it again, and now we see the summaries here. So as you see, the generated summaries is weaker than the previous summaries, right? So I just demonstrated you can play with different algorithms of interpolation and you generate different summaries. Yes, I hope you enjoyed playing with HiFrog. So tomorrow we'll continue with seeing some more interesting features of HiFrog. We also see some examples with our tool approver, where we are going to verify different revisions of the program. So basically, when the assertion stays the same, but you see different revision of the same program.
Thank you for all three of you. You guys, this was really well organized, so we really appreciate it.
Oh,
Thank
yeah.
you.
Thank you very much.
Thank you.
Thank you.
So Sepideh, you can end the recording.